Hello students, I am Dr. Tanmoy Biswas. I welcome you all in my channel TanmoyChem. Today's topic of discussion is on MCQ and the question is in front of you. Among the following, which of the molecule has the lowest rotational barrier for this carbon-carbon double bond? So I am saying this and these four double bonds. By the way, I have given a little clue. So I request everyone, please pause the video, try by yourself, and whatever answer you get, please write in the comment box along with few words as explanation. I believe you have tried, so let's start. Now question, actually they are CC double bond and we know CC double bond rotation is restricted. Why? So if you look at here in alkane, these alkane molecules CC rotation is allowed. Why? Because these alkanes are made of head-on overlap. I repeat the statement, it is head-on overlap between these two sp3 hybridized orbital. So you can see CC rotation allowed. Now if you look at this alkene, this is a double bond, means one sigma plus one pi bond. By the way, in this case of pi bond, the CC rotation not allowed because these pi bonds are made by side-wise or parallel overlap of the p orbitals. Now here you can see this. Now if you want to rotate this bond nearly 30 degrees, so this pi bond will not remain, this bond will break. So in this case you can say rotation restricted in case of alkane. Although if you rotate this molecule 30 degree, similar this second bond will exist. By the way, do not get confused, all six substituents are hydrogen. So the rotational barrier because of this bulky group is not mentioned here. So what we understand? That carbon-carbon double bond cannot rotate smoothly, although carbon-carbon single bond can be rotated, and this concept is utilized here. So if you want to rotate a carbon-carbon double bond, how it is possible? Obviously by resonance. So you can see here this bond can come there and there is a charge separation, and okay fine, this canonical form, but we understand that the charge separated canonical form has lesser contribution in the overall electronic distribution of the molecule. So in the overall resonance, these canonical form, this charge separated canonical form generally have less contribution. I repeat the statement, generally have less contribution. But how can I increase the contribution of this charge separated form? Obviously by stabilizing these two charges. So if these two charges are stabilized, so then this canonical form has more contribution, and that case this CC rotation possibility will increase. So this is actually the fundamental concept learned behind this problem. Now let's go back to our main problem. So here actually four substances are given. As I told, these carbon-carbon double bonds are under consideration. Now if you look at here, option A and option C, they are unsymmetrical substances. So you need to be little careful regarding this. So question, which side you move this arrow, right side or left side? These will be decided the factor after moving the arrow, any side, how much stability I am getting. So for example, if you rotate the arrow this side, then what will happen? So you may expect sir, negative charge here, positive charge there. So this side is aromatic because 6 pi electron according to Huckel's rule, I mean 4n plus 2 number of pi electron theory, and this side you can say anti-aromatic. By the way, arrow means aromatic and this is anti-aromatic, this is aromatic. I want to mention in this way. If you think in a opposite way, that's also true. Means if you think in this way, similarly positive charge is here, negative charge is there. So this side is then my aromatic because 2 pi electron, and this side 8 pi electron, so you can say anti-aromatic. So this is the thing, in this case we understood, and in this case symmetrical doesn't matter. Now here also same thing. So you can move the arrow this side, so negative charge will come here, positive charge will go there. What is the benefit? Benefit you can see here. So this case actually all are student, it's their resonance in canonical form. So now, so here negative charge comes, here positive charge. Negative charge, by the way, I have already discussed a dedicated lecture on this topic. You may visit for further learning. By the way, all cation anion case I have added specifically, uploaded specifically video on this. You may visit if you want to learn further. Now it is actually, this part is, if you look at it, is stabilized. How? Because here 2 pi electron, here also 2 pi electron, and this negative charge means actually 2 pi electron. So total this side 6 pi electron, right side 2 2 2, positive charge means no electron, again 6 pi electron. So this side is aromatic, this side is aromatic. So both side is aromatic means it is a stable. So in this case the CC bond resonance has more, and this CC bond has more partial single bond character. Okay, so partial single bond character it will show. Next, if you look at here, as I told, this side aromatic, this side anti-aromatic. So overall no stabilization, will not discuss. If you look at here, in this case this side is anti-aromatic, this side is aromatic, so overall no significant stabilization, so such kind of resonance will not take place. Now look at the option D1, this side is actually anti-arrow and this side is arrow, so overall no stabilization. So in case of option A, B and D, the resonance is not bringing overall stabilization at all. So consequently resonance probability will be less in option A, B and D. But look at option C. So because of this resonance, both of the rings are getting aromaticity according to Huckel rule. I mean 4n plus 2 number of pi electron, cyclic, planar, conjugated at 4 points. So I've already discussed a dedicated video. If you want to learn further about Huckel rule, you may visit. So here, so both, because of resonance, two canonical, so one canonical form we are getting where two rings are stabilized because having Huckel number of pi electron. So in this case this resonance contribution more and this resonance contribution more means the percentage of this single bond resonance structure will more, so more partial single bond character will be observed here, and since the CC single bond rotational barrier is very low, so in this case compared to option A, B and D, this case the CC rotational barrier will be less because single bond character is more. So this is the overall discussion. So which one will have the lowest rotational barrier for CC double bond? So option C is the right answer. Now student, in this case I suggest you that such kind of problem need to be understood very clearly, and you cannot get that much time in exam hall to draw everything. You need to think about in your mind that okay, if plus charge here, minus charge here, 4n pi anti-aromatic. If you think this side plus charge, this side minus charge, this side plus charge, okay, one part aromatic, one part anti-aromatic, and this is the unsymmetrical one. But if you look at here, okay, this side, so this is aromatic, again this side aromatic, so take this first and look at the symmetrical substance. There is no specific stabilization, so one side aromatic, another side anti-aromatic in both cases. So obviously this one, I know in exam hall you'll not get that much time to draw. Now you need to do all the calculation in your mind. For that purpose you have to study more and you have to practice more. And as for practice, I request everyone to draw all the structure by yourself on pen and paper, because remember, structured drawing increases your memory as well as understanding. So please try. Now this is the overall discussion. I believe this video will be useful. Thanks for watching. If you really enjoy my content, please help this channel to grow, and please do not get confused about the logo of my channel. I request you to read this part in case of any doubt regarding the logo and the message associated with this logo. See you in my next video. Bye bye.